We physicists have waited 100 years since 1916 for this photograph. It is a region black holes might just be one of the most fascinating and mysterious phenomena in the universe. They are massive beasts in terms of power, but at the same time virtually invisible to us, and a black hole weighing perhaps 2 to 4 million times the mass of the Sun. But because of the research that was put into them over the last couple of decades, we've gone from knowing absolutely nothing about them to getting to learn more and more up close and personal. And while things have just gotten crazier, Michio Kaku just announced that we've finally gotten a look at what's inside a black hole. And this new information brings light to the details the world of science might have missed all along. Join us as we dig deeper into black holes and unveil what's inside space's big bad. Before we get into the details of what Michio Kaku found, we have to talk about the firsts. Even though most of us have some idea what black holes are, there are still some gaps in the right information. You see, in 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the concept of black holes was purely theoretical. It took another 50 years for the scientific community to find evidence that black holes actually exist. This happened in the 1960s, and they were studying the Cygnus constellation and noticed an oddly bright blue star that was emitting X-rays. This star wasn't a stagnant object, it was going around a giant black something. Upon further investigation, it was found that the X-rays weren't just moving around on their own but were being sucked into the black thing they were orbiting, thus the name black hole. This discovery was significant because it provided proof that black holes actually exist and that they weren't just a figment of Albert Einstein's wild imagination. While that was great, it's also meant that there was this unreal entity in space that we urgently needed to know more about. So researchers all around the world got to work. This black hole was named Cygnus X1, and it is located in the constellation Cygnus, about 6,000 light-years from Earth. It was no small discovery. It's about 14 times brighter than the Sun and incredibly dense, which causes it to have a strong gravitational pull. The gravitational pull is so strong that not even light can escape it. This is why it is called a black. The idea of a black hole is both intriguing and frightening. A black hole is a region in space where gravity is so intense that nothing, not even light, can escape its pull. Anything that ventures too close is inevitably drawn in, never to be seen again. This danger only heightens the importance of understanding black holes thoroughly. Was this our limit, or were we just beginning to explore? The latter proved true. After discovering Cygnus X1, scientists began searching for other black holes, uncovering evidence suggesting there could be over 100 million black holes in the Milky Way alone. Due to their elusive nature, we lack an exact count, but there are likely millions in our galaxy, underscoring the need for further study. To break it down, the primary concern with black holes is their gravity. The gravitational force is so powerful that it compresses anything entering it into a singularity. Essentially, black holes act like cosmic vacuum cleaners, drawing in everything around them. One particularly alarming aspect of black hole research is the fate of anything falling into one. It would be stretched into a single line, a process that would cause death long before reaching this final form. Clearly, no one should approach a black hole, yet their prevalence raises questions about potential danger. The closest black hole to Earth is 1,500 light-years away, close enough to warrant concern. In 2021, scientists released the first clear photograph of a black hole, specifically an 87 black hole. This black hole was photographed over several nights, and each image provided more evidence. Researchers had to stitch these images together to create a complete picture, revealing that black holes have 3 layers. Contrary to popular belief, a black hole is not just a singular void. It is much more complex. To reach the central nothingness of a black hole, one must pass through the first 2 layers. The outermost layer is known as the event horizon, which, while in the first layer, it's the point of no return. Once you pass the event horizon, there's no turning back, and you will be sucked into the black hole. It only gets worse from there on out. The second layer is the photon sphere, which is the region where light orbits the black hole. Any light that enters this region will be trapped and will not be able to escape the black hole's gravitational pull. Finally, we come to the third layer, which is the singularity. This is where everything that enters the black hole gets compressed down astronomically until it becomes a singularity. The singularity is a point in spacetime where the laws of physics as we know them break down, and we just can't predict what happens next. At the singularity, the density is infinite, and the laws of physics as we know them cease to exist. Now what makes all of this infinitely worse is the fact that every single black hole you study will be entirely different from the last. Sure, they do tend to follow the same three-layer concept, but the way they function could be vastly different. Now, if this were anything else, all we'd need to do is hop back on those telescopes and just study the problem at hand in detail. But with black holes, you can't really do that. Scientists can only study black holes indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe like the Voyager inside a black hole is not possible because anything that enters the event horizon is pulled towards the singularity, where it is compressed to an infinitely small point. So you can't exactly waste billions of dollars just to get a glimpse every time, because the second the probe gets close enough, it'll just crush into nothingness. Because of that glaring problem, scientists are left with no option but to study these objects in a two-dimensional way, even though they are three-dimensional phenomena in reality. To make matters even more challenging, there are also the two problems of every black hole being unique and the laws of physics as we know them breaking down when we try to explore the inside. This means that the traditional methods of scientific inquiry don't really apply to the study of black holes. That doesn't mean that the researchers haven't been busy. There are lots of different theories and explanations of black holes, and with each one, things get more and more interesting. One of the most compelling theories about the formation of black holes is that they are created from collapsed stars. When a star exhausts all of its fuel, it can no longer produce enough energy to counteract the force of gravity that is constantly pulling inward. As a result, the star begins to collapse in on itself, holes, and with each one, things get more and more interesting. One of the most compelling theories about the formation of black holes is that they are created from collapsed stars. When a star exhausts all of its fuel, it can no longer produce enough energy to counteract the force of gravity that is constantly pulling inward. As a result, the star begins to collapse in on itself, becoming smaller and denser as it does so. If the star is massive enough, this process can continue until it becomes a singularity. To understand the nature of black holes in depth, NASA scientists turned their attention to the core of the galaxy in 1987. Astronomers observed a super-powerful whirlpool of super-hot hydrogen gas that was spinning at an astonishing rate of 1.2 million miles per hour. The sheer force of this spinning disk of gas should have caused it to violently fly apart in all directions, but it didn't. Scientists deduced that there had to be a colossal mass concentrated at the center of the galaxy to prevent this from happening. This massive object weighed as much as 3 billion suns and could only be a black hole. But that's not the only theory or black hole spin. In 1963, the New Zealand mathematician Roe Kerr used Einstein's equations of gravity to provide the best description of a spinning black hole. Kerr showed that a spinning black hole wouldn't collapse into a point as previously thought, but into a ring of fire or a thin disk. The disk would be spinning so rapidly that centrifugal forces would keep it from collapsing. This spinning disk of matter is called the ergosphere, and it is the region surrounding the black hole where the laws of physics start to break down. But the most intriguing feature of Kerr's solution was that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This is a theoretical passage through spacetime that connects to separate regions of the universe or even to parallel universes. The idea is that if one were to fall into a black hole, instead of being crushed to oblivion, one would be sucked down a tunnel through the ring of fire and shot out a white hole in a parallel universe. To understand how this works, we need to look at the concept of spacetime in Einstein's theory. Space and time are not separate entities, but are interconnected, forming a four-dimensional fabric called spacetime. Objects with mass warp this fabric, creating a gravitational field that causes other objects to move towards them. Now imagine a sheet of paper representing spacetime. If you place 2 points on the paper and draw a line between them, this is a representation of how objects move through spacetime. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind